Welcome to the hands-on session on crystal graph convolutional neural networks. So in this hands-on session, we'll build the CGCNN model mostly from scratch, and we'll use it to train a data set that contains crystal structure information and some elastic properties. So let's get started with the notebook. This notebook is split into three sections: data loading and analysis and model construction. So these two are two important aspects because we have our crystal structure information and we need to use it to create graphs of the crystal structure and then understand what the node features, edge features, etc. are. And then the model construction will also take some time, but the model training and evaluation will be as usual, and we'll quickly go through the last part. Let's get started. We'll start with importing the usual packages: random, time, pandas, numpy, matplotlib, torch, etc. And another important thing is this implementation will be based on Pytorch. So we'll be using torch and another package called torch scatter. And finally, we have also written a utils module. So this is a module that is not there by default in Pytorch, but we have written it using classes of Pytorch to build on more classes. And we have this utils module in the same directory as our CGCNN notebook. So we can directly import all the functions and classes defined here in this utils module directly from the notebook. So let's perform all the imports. And once this is done, let's set the random seeds to ensure reproducibility. And now let's take a look at our data set. So the data set is present as a JSON file. Pandas can again be used. The read JSON function can be used to import this JSON file as a data frame. So let's do that, and let's look at the first 5 data points in our data set. Basically, our data set contains 4 columns: positions, numbers, cell, and y. Y is our target label, and this is the logarithm of the GVRH value, basically the shear modulus averaged by the VRH method, and this basically contains 10,987 data points. And because the GVRH value ranges over multiple orders of magnitude, we have taken the logarithm value of this. And our training features are basically the unit cell information of a crystalline structure. So basically we have positions of different atoms, the identity of different atoms denoted by their atomic numbers, and the lattice vectors of each cell. Let's look at these in some detail. So if we look at the first cell, that is the 0th row and 0th column, let's print this out. We see it's a matrix with 3 columns and 5 rows. These basically represent the 5 different atoms present in a unit cell. Similarly, the second column, corresponding to numbers, represents the 5 atomic numbers in the order of the atoms that appear in the positions matrix. So the first position corresponds to an atom with atomic number 20, that is calcium. The second atomic position corresponds to an element with atomic number 32, and so on. And finally, the third column represents the lattice vector. So basically the lattice vector A is 4 in the x direction, 0 in the y direction, and minus 1.5 in the z direction, and so on. So the first 3 columns provide information about the unit cell of a crystalline structure. Now in a graph neural network, we need to convert this crystal structure into a graph. To do that, we have written a function called matrials-dataset that is present inside the utils module. And if we look at this this class, we actually inherit the dataset class of Pytorch to build our material dataset. And the init function of the material dataset takes 3 arguments. The first is a file name, which basically should be the file name of the data that we are giving. And note that this function is written such that it can only read JSON files, and the JSON file should also contain data in a particular format which should contain keywords like position, numbers, cell, and so on. So if you want to use this model with your custom data, either you have to convert your dataset into a JSON format in this formatting, or modify the materials dataset code. So the first argument is the file name. The second argument is the cutoff radius, which basically means how far around an atom should we look to find out neighbors for that atom. Basically, say we have an atom in a crystal structure. All atoms that are within 4 angstrom of distance from that atom are considered as neighbors of that atom. And finally, num Gaussians, which is the number of Gaussians in the edge embedding. We'll look into the details of cutoff and number of Gaussians later in the notebook. So let's run this. And since it contains a lot of structures, this might take a while to run. So it is basically converting all our structures into graphs, and we'll further see how the graphs look like, how to use the material dataset attributes and methods, etc. And note that the instance of the materials dataset we are creating is named dataset. So this line of code has completed running. Now the dataset instance contains an attribute called data, which again contains a list of dictionaries. So we can convert this into a data frame, and let's look what this data attribute contains. We see that the first 4 columns are the same as the JSON file columns. It's position, number, cell, and the target Y values. There are a few more columns created. So one is called the atoms. This column basically contains an ASC.atoms object. So ASC is atomic simulation environment, that is a suite of packages useful for materials code. So we'll be using this later on in the course. And this ASC package has not been imported in this notebook. So if you see, there are no imports for ASC, but the utils module that we have created makes use of this ASC atoms object and some other functions within ASC. So this atom column contains the ASC atoms object. Similarly, edge source and edge destination are 2 more columns that basically contain some information about the edge. We'll look into more details of this. And there's an edge length column basically denoting the bond lengths corresponding to each bond that the edge represents. So these are a few more columns that have been created within the dataset instance. And another important thing to note is our dataset instance is actually iterable. So we can access certain instances of our dataset by exactly by the way we access elements of a list. So we can index it like a list. So let's run dataset within square bracket 0 to see what is the 0th element of our dataset object. So we see there is quite a lot of information, something named node feature which contains a tensor. There's an edge feature that contains a tensor. There's another attribute called edge source, edge destination, target value, atoms, which basically contains the ASC atoms object, and so on. Now let's take a look at the distribution of the data. So this line of code basically iterates over all the elements of our dataset because our dataset is an iterable, and it prints the x.target. So basically x iterates through each element, and there is an attribute called target within each element. So we see here, this is the target value basically, which is a Pytorch tensor. So the target value, since the target value is a single number, we access the first element, which is a scalar, and we plot these values as a histogram. Let's see what's the distribution of our target value. So this is how our log GVRH is distributed. And the thing to note is that this log GVRH takes continuous values from 0 to 2.5, which basically means we are trying to solve a regression problem. So our log GVRH value can take any float number. Now let's look at each feature within our dataset instance. So as we saw previously, there are basically a few features named node feature, which contains information of a node of a structure. So let's look at the following lines of code and we'll understand these one by one. So let's call the first instance in our dataset variable sample. So sample is the first instance, And let's use this plot sample function that is defined in the utils package and plot this first sample. So we see this is the unit cell of the crystal structure that is the first data point, and this represents the graph of this unit cell. So, and notice that the cell dimension, so in the x direction the unit cell is about 4 angstrom. So if we create a sphere of 4 angstrom around this, whatever atoms come within this sphere are termed as neighbor of this dark blue atom. And another thing to note is that this is only a unit cell which will get repeated in the x, y and z directions, and these blobs yellow and blue are in 3 dimensions, so they are not necessarily on a single plane. So for this blue atom within 4 angstrom we might see just 4 atoms within the unit cell, but if we see the periodic boundary images of this, there might be more than 4 neighbors, and a single atom can be connected to a given atom more than once through an edge, and this graph representation only shows a single edge between 2 different atoms. Now let's look at the sample's node feature and see what is the shape of this. So this basically means that every node in our graph, so every atom is represented as a node, and every node in our graph is represented as a vector of 119 dimensional vector. And since there are 5 atoms in our crystal structure, the node feature has 5 rows and there are 119 columns. And another important thing to note is that graph visually looks like this, but to a computer graph has to be represented in form of numbers. So the way a graph is represented here is in the form of 2 matrices. One matrix contains information about the nodes and the other matrix contains information about the edges. And this node feature basically is the matrix that contains node information. And let's print out the node feature. So sample.node feature 0. So we are basically printing the 0th row of our node feature. There are 5 rows corresponding to 5 different atoms. And let's see what happens here. So this is how our node feature looks like. There are 119 numbers because there are 119 elements in the periodic table, and the atomic number corresponding to that element is marked as 1 and all other numbers in the vector are marked as 0. So our first atom in our crystal structure is calcium. So this is represented as 119 dimensional vectors where all except the 20th element is 0 because calcium's atomic number is 20. And we can access this 20th element because indexing starts with 0. So the 20th element has index of 19. So if we print out sample node first row and index of 19, we get a tensor 1, basically meaning the 20th instance or 20th element of this vector is 1, all others are 0. Now just as we looked at a node feature, let's look at an edge feature. So in our implementation, all the neighboring atoms are connected by an edge, and an edge basically represents a bond. So let's see how an edge feature looks like. So every bond is represented by a 40 dimensional vector, and this was fixed as a hyperparameter whenever we defined our materials-dataset class. So we had set num Gaussians as 40. This basically translates to every edge vector is represented as a 40 dimensional vector, and there are 58 edges in our crystal structure. In the representation of our graph, we did not show multiple edges because we showed only edges within this unit cell. But with the periodic image, there are 58 edges. That's why our edge feature contains 58 rows, and each feature contains is a 40 dimensional vector. That's why there are 40 columns. Now also let's look at the first instance of our edge feature, basically the first row of this matrix. And we see this is how our edge feature looks like. Now let's try to understand how we converted a single bond length into a 40 dimensional vector. A bond length is a scalar. How did we convert a scalar into a 40 dimensional vector? So to do that, we used something called a Gaussian basis. So to show you how this works, let's run this piece of code. So this piece of code basically runs a plot to visualize how we converted this scalar into a vector. Let me run this. Now let's focus on this plot. Our cutoff radius was 4, basically meaning all atoms within a radius of 4 angstrom are considered as neighbors. Now let's say that there are 2 atoms that are separated by 2.5 angstrom here. Now how do we convert this bond length of 2.5 into an n-dimensional vector? To do that, we first fix the value of n. So we first fix how many dimensional vector we want to create, and for simplicity here we have considered n is equal to 10. That means we want to convert our bond length scalar into a 10-dimensional vector, for example. Now here, since we want to convert it into a 10-dimensional vector, we create 10 equally spaced Gaussians within our cutoff radius. So our cutoff radius is between 0 and 4. So our cutoff radius is 4, and between 0 and 4 we create 10 equally spaced Gaussians, and our bond length is 2.5. Now every Gaussian has a numeric value at x is equal to 2.5. For example, if you look at the first Gaussian that starts at 0, has almost a value of 0 at x is equal to 2.5. Similarly, the second Gaussian also has a value of 0. Similarly, if we go on, we see up to this red Gaussian also has almost 0 value at 2.5. However, the purple one has a non-zero value about say 0.1. Then the brown one has even a higher value, so about 0.7, and so on. So every Gaussian that we have created has a value at the given bond length, and we pick up these values to create our n-dimensional vector. So this is the code for placing the Gaussians at different centers and converting them into a vector. So if we run this cell, we see that the values taken by the first n Gaussians are 0, 0, 0, 0.001, then 0.071, 0.677. This basically means our bond length of 2.5 has now been converted into a 10-dimensional vector. So this is how we use Gaussian basis set to convert a scalar into an n-dimensional vector, and the number of Gaussians is equal to the dimensionality of the vector that we want to convert. And this is all about the node feature and the edge feature. Node feature basically contains information about the atom. Edge features basically contain information about the bond length, and which atoms are bonded to a given atom are determined by the cutoff radius, which we have set to 4, and the dimension of our edge embeddings we have set to 40. Apart from this, we have 2 other variables. One is called the edge source and the other is called the edge destination. Let's run these 2 and see what these contain. So edge source looks something like 0, 0, 0, 1, 1, 1, 1, etc. And edge destination is also a similar dimensional vector. This basically contains information about what are the starting and the end atom for each edge. For example, the first edge starts at atom 0, the atom which is at index 0, and ends at an atom which is at index 1. Similarly, the second edge starts at atom 0 and ends at atom 4. So edge source and edge destination contain information about which 2 atoms an edge or a bond connects. So this is also an important information that we'll be using in our graph network. And finally, plotting a sample. This is how we can plot this sample that we have already seen. Now that we have obtained a clear idea of how our data looks like and how it has been converted into a graph, let's go ahead with splitting our data into train, validation and test split. Now we can also use scikit-learn, but we have used this random split method within TensorFlow because it takes care of it ensures that all our data is in the tensor format. So we just provide the data set, which is an instance of our material dataset class, and then we say the first set that we should obtain should have 0.8 of the total data set. That is basically our train set, and 0.1 are our validation and test set. So let's run this and print out how many numbers of data points are there in our train, validation and test set. We see there are about 8,700 training examples and 1,100 validation and test examples. Now the next thing as usual is setting up batches. So we want to set all the data points within a batch to our neural network, and then after our neural network has seen all the data points in this batch, it will update its weights and biases. So we have set a batch size of 32. This is again a hyperparameter. We start with 32 and we use our data loader class, which is already imported from Pytorch. And we give it the training set, the batch size, and we also provide a collate function. This collate function is defined in the utils module, and this basically says about, it gives some information about how our data points are distributed within a batch. So, we will look into more details of how a batch looks like. So, we have loaded a train batch, a validation batch and a test batch, and we have shuffled all our training data, but for validation and test we have not shuffled the data because that is not necessary. Now that our batches have been set, let us look at how each batch of data looks like, and here we will discover something unusual from the usual neural networks. So, each batch again contains a node feature, edge source, edge destination, target, and a batch. So, this batch actually comes from the collate function. We will discuss that a little further in the notebook. So, basically now each node feature contains n rows and n node feature basically the dimension of our node feature, which is 119. Edge feature contains m rows and 40 columns, and n and m represent to the number of atoms and edges that are present in the total batch, not in a given structure. So, let us look at one of the node feature shape and edge feature shape within a given batch. So, our test loader contains a batch. So, we iterate over the test loader and get the first instance of our batch in the test loader and print out that batch's node feature and the shape of the node feature. So, we see here this batch contains 302 rows and 119 columns as usual, and similarly the edge feature for this batch contains 5778 rows, because there are multiple structures and each graph need not contain the same number of nodes and edges. Usually the number of edges are much more than the number of nodes. That is why in our given batch we just have 302 nodes corresponding to different crystal structures, and 5778 edges again corresponding to different crystal structures. And the part that is different from usual neural networks batch is that every data point or every crystal structure can have multiple nodes and edges, and these number of nodes and edges are not fixed across structures. For example, some structure can have 5 nodes, some other structure can have 15 nodes depending on the number of atoms that structure contains. So, basically we need to give the information about which of the rows correspond to a single structure. So, that is obtained within this batch.batch variable. So, let us print out this batch.batch. This basically is a sequence of numbers, and the first 5 zeros mean that the first 5 nodes in our batch correspond to the first crystal structure. Similarly, the second 2 nodes correspond to the second crystal structure, and so on. Now, this is all about how our data is structured and how we put them into batches. And now let us go into the architecture of our convolutions in our graph neural network and the final crystal convolution graph neural network. So, we make 2 classes, both inheriting from the NN.module class. The first class is for graph convolution, which defines how convolution or message passing happens within a graph. Now, let us see how we have defined this graph convolution. So, basically we inherit from NN.module, and in the init function we provide the dimension, the node feature dimension and the edge feature dimension. So, for us our node feature dimension is 119 and edge feature dimension is 40. And within the init function we define the first layer, which is NN.linear, basically meaning it is a dense layer, which takes in 2 into node feature dimension plus edge feature dimension, basically meaning it takes in a vector that contains 2 into 119 plus 40 units, and we will see why this is so, and it outputs another vector that contains 2 into node feature dimension, whose dimension is 2 into the node feature dimension, basically meaning 2 into 119, and we define 2 batch normalization layers, or we define two variables to perform batch normalization. The first batch normalization has 2 into number of node feature dimension, and the second batch normalization has a dimension of node feature dimension. Basically the first one containing 119 into 2 and the second one has a dimension of 119. Now let's look at the forward method, which basically tells us how data flows through this convolution. So this forward method takes in a few inputs: the node feature, the edge feature, edge source, and the edge destination. And the first thing that it does, it clubs a few matrices, which is node feature within brackets edge source, node feature within brackets edge destination, edge feature, into a single matrix. So to look at how it is done, let's see an example run of this line of code. So basically we have our sample, which was defined previously. Let's access the node features, the edge feature, edge source, and edge dimensions from this sample. So let's say our trial node feature is sample dot node feature, and similarly our trial edge feature will be sample dot edge feature. Our trial edge SRC will be sample dot edge SRC, and our trial edge destination will be sample dot edge destination. And let's print out the shape of each of these features. So trial node feature dot shape, trial edge feature dot shape, trial edge SRC feature dot shape. Let's remove the feature here. Just a naming convention. And trial edge DST dot shape. So basically our first crystal structure contains 5 atoms, that's why 5 node features. It contains 58 edges, that's why 58 edge features. And because there are 58 edges, there will be 58 sources and 58 destinations. Now this line of code basically takes in the node feature corresponding to every edge source, the node feature corresponding to every edge destination, and the edge feature, and combines them column wise to create a single matrix. So to understand what these does, let's first print trial node feature. So basically this is our node feature, and if we pass it trial edge SRC, this basically puts the node feature corresponding to every edge source in a given matrix. And if we look at the shape of this, this will have as many rows as there are number of edge SRC, or as there are numbers of edges. So we print the shape of this. There are 58 edge sources, that's why there are 58 elements in this matrix. Similarly, trial node feature within brackets trial edge destination will also be a similar dimensional matrix. And finally, our trial edge feature will also have the same number of rows, because basically these 3 variables have as many number of rows as there are edges. Now if we concatenate all of these, so if we use this line of code and say save it as m trial, and print the shape of M trial. And instead of node feature, we have trial, 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 trial. Underscore. And the dimension equal to 1, meaning we want to concatenate these matrices column wise. So the number of rows in the final matrix M trial will be constant, but the number of columns would be 2 into 119 plus 40. So let's print the shape of this. Okay, trial node feature, feature, feature. Trial edge feature as well. Okay, so now if we run this, we see there are 58 rows but 278 columns. So let's comment it out here. So M has a dimension of num edges, comma 2 into or 2 into node embedding plus edge embedding. So this is the dimension of the matrix M. Now we pass this matrix into the first dense layer, and if you notice here, the first dense layer has an input dimension of 2 into node feature dimension plus edge feature dimension, which is basically what we have obtained as M. So Z takes in this M, and so self.linear takes in this M and returns the value to Z. Now Z should be a 2 into node feature dimension dimensional vector. Basically there should be 2 into node feature dimension of columns here, and the number of rows will remain constant. After that, this line of code basically splits this. So let's write the dimension here as well. So here the dimension would be num edges number of rows, but 2 into node embedding dimension of columns. Now after we have obtained Z, we are splitting Z by the number of columns into two matrices. Basically we have 2 into node embedding dimension of columns here. We are obtaining 2 more matrices, both with the same number of rows but half the number of columns. So Z1 corresponds to a matrix of dimension this, and similarly Z, so this is Z1, and Z2 corresponds to a matrix of dimension this as well. So these are the dimensions of Z1 and Z2. We pass Z1 through a sigmoid, we pass Z2 through a soft plus, and then we do a Hadamard product. So Hadamard product is basically element wise multiplication of two matrices. So Z again will contain dimensions of this. So Z again has dimensions of number of edges into number of node embeddings. So this is basically 119, and number of edges will vary depending on how many atoms or how many bonds are there in your crystal structure. And finally, we pool the features. Pooling basically means we can convert or we can change one of the dimensions of the matrices. And we have mentioned that we are pooling along dimension 0, basically meaning we are pooling along the rows. So now we can convert this Z matrix, sorry, the Z matrix is here. We can convert this Z matrix into a dimension of node feature, into a number of columns corresponding to node features. And how we do that is based on our edge source. So this basically outputs again a matrix of num nodes comma node embeddings. So you have converted a matrix with num edges rows into num node rows. Basically for our first sample, till here Z contained 58 rows, but after the pooling Z will only contain 5 rows here. And finally we have obtained this Z. We pass this Z through batch normalization and we add the existing node feature. Now because we are doing this addition, Z should be compatible for addition, and that will only happen when the number of rows and columns are same for Z and node feature. And clearly node feature contains number nodes of rows and number of embeddings of columns. So once we add this and we pass it through soft plus and return this value. So in short, what the entire convolution is doing is taking information of nodes that are connected by edges and somehow combining them and then adding them back, then pooling them, so that we get a matrix of that has same dimension as the number of node features, and then we are adding the node features to the convoluted node feature that we obtained as Z. Basically this means that our nodes are learning from their neighbors, and the more times we do the convolution, the more the information of farther neighbors each node will contain. So this is basically in short what convolution does. Now once we have defined our convolution, we can define our full graph network architecture, which should perform convolution and also pool the data that is present in the convolution and pass it through a dense network. Let's see how our CGCNN is defined here. Again we inherit from the nn.module class. Our init function takes the node feature dimension, edge feature dimension, node hidden dimension, number of convolution layers, so how many times we want to do the convolution, and the fully connected feature dimension. So this is basically the number of nodes in our fully connected layer, and node hidden dimension basically converts our node feature into a shorter array of dimension 64. Let's see how that is done. So in the init function we have defined self.embedding, which is a dense layer that can convert a node feature dimension into node hidden dimension. Basically it can convert 119 to any given dimension that we want, and here we have provided node hidden dimension to be 64. And then we set up the convolutions. So we have to provide how many convolutions we want. We loop through it, and to this convs array we add a convolution the number of times we want a convolution, and this graph convolution is defined previously. So to this we give the node feature dimension and edge feature dimension, and finally we create a list of these layers and put it in nn.module list and save it as self.convs. And finally we have a dense layer that has input dimension of node hidden dimension and FC feature dimension of the output dimension. Basically once we have performed the convolution and obtained a vector of this dimension, we again pool it and pass it through a dense neural network which has a hidden dimension of this, and finally in the output layer we will pass this vector into an output layer that outputs a single value, because we want to predict the log GVRH which is a single number, and we do not want to put any activation function through this. Let's again reconfirm the same workflow in the forward method. So basically first we take the entire batch, convert it into, we pass it through a neural network and convert its dimension to create our, to change our edge, to change our node embeddings. And then we apply the convolutions. So self.convolution number of times that we have already defined here, self.convolutions. And finally we get our message passed learnt graph. We pool our graph into a single vector. So basically for pooling we have used torch_scatter mean. We take our node feature and pool it along the rows. So the dimension is 0 here. Basically we are pooling along the rows to convert this into a single dimensional vector. So now crystal feature has been converted into a one dimensional vector. Now again we pass this one-dimensional vector into our fully connected neural network, and finally get the output here. So this is in short how the CGCNN works. It takes in a graph, performs message passing. After message passing, we get a matrix with as many number of rows as there are number of nodes in the graph. Then we pool that graph or we pool that matrix into a single row vector or a one-dimensional vector, and then we pass it through a dense neural network and get our output. So this is the full definition of CGCNN. Now the final part is to create an instance of our CGCNN model and train the model. So we have set the node feature as the number of columns in the node features, the edge, the num node and the num edge feature as number of columns in our edge features. We have set number of convolutions to 3. This is again a hyperparameter, and then we create a CGCNN model using these parameters. Okay, we have to run the CGCNN class. So we run this, and we have to run the graph convolution as well. Yeah, so we run graph convolution, we run the CGCNN model, and then we create an instance. Our instance is created. Now the final part is the usual training. So as usual, we define a device. So if you want to run it on GPU, it will directly detect CUDA. Otherwise, it will provide device as CPU. Then we move the model to our device, the criterion to our device. So before that, we have to define our criterion. So we have defined our criterion to be MSE loss, mean squared error loss, because we are solving a regression problem, and our optimizer is torch.optim.adam, and we have provided it the model parameters here. So let's first compile our model, that is basically declaring our optimizer and criterion. And once that is done, let's move the model and criterion to the device. And finally, as usual, we define a training loop and a evaluation loop, which has already been discussed. So in short, we define a function called train. We pass in the model, the data loader, criterion, optimizer and device. We put our model in the train mode, and then we predict our values for the batch. Then we calculate our loss, we calculate our MAE. Once we have calculated our loss, we compute the gradients. Before computing the gradients, we set all the gradients as 0. Compute the gradients in loss dot backwards, and then take a step in the optimizer, and then we add the losses to this array, epoch loss and epoch MAE, and finally we return the average value of epoch loss and epoch MAE. So this is our training function. Evaluate function is the same, just that we do not do back propagation. We put our model in the evaluation mode, and we need not update our optimizer. So we again define our evaluation loop, and finally we have to run our training. So let us run this training for say 10 epochs, and let's run this. This might take a while. So basically we have set the validation loss to be infinity, and every time we calculate the train loss, train MAE, validation loss, validation MAE, we check whether our validation loss is less than the best validation loss, which will be true for the first instance. And every time the new validation loss is lower than the best validation loss, we update our best validation loss and save the same model as elastic model.pt. And we are training it for 10 epochs, and we see that the training time will be a little slower because we are performing convolutions and then passing it through a neural network, and we are optimizing all the weights within the convolution and the neural networks. So this might take a while. So our training for 10 epochs is done. And now let's plot how the training and validation loss and accuracy vary with epochs. So this is the code for plotting that. And we see that the training and validation loss have decreased, but they have not yet reached a minimum. So we can train this model further. In the interest of time, we'll not do that, because but you can try it on your own. And once the model is trained, we have saved the best model which has the lowest validation loss. So probably we would have saved the model at epoch number 8. So we'll load our model which has the lowest validation loss. So this is the code to load the model. And then we evaluate the model on our test loader and print out the test MA. So basically we find the test MA to be about 0.1119. And we can also create a parity plot based on the predictions. So this is the code to create a parity plot. Let's run this and see. So as of now, this is how our actual log GVRH and the predicted log GVRH vary. And we can play with the model. We can increase the number of convolutions or decrease, change the number of edge embeddings and node embeddings, etc. And we can tune the hyperparameter so that the model performs the best. And we can also increase the number of epochs as well. So this is the end of the short demonstration of how a CGCNN model works. Thank you for joining this tutorial.